Good afternoon, class. We are looking at Chapter 3, Polynomial and Rational Functions, and here's 3.4, Complex Zeros, Fundamental Theorem of Algebra. We've covered power functions, polynomial functions and graphs, dividing and real zeros of polynomial functions, and now complex zeros of polynomial functions, and the objectives are: use the conjugate pairs theorem, find a polynomial function with specified zeros, find the complex zeros of a polynomial function. So recall, a polynomial function is in the form of f of x or p of x equals a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 all the way to a sub 0. A sub n x to the power of n is the leading term. A sub n can't be equal to 0 is the leading coefficient. N is a whole number, 0, 1, 2 to infinity, and domain always all real numbers. For example, a polynomial of degree 1, you're all familiar with. Y or p of x equals mx plus b is a linear function. A polynomial of degree 2, y or p of x equals ax squared plus bx plus c is a quadratic function, and the vertex is located at x equals minus b over 2a, and then you plug it in. F of minus b over 2a gives you the y coordinate of that function. Degree of the polynomial function f of x is n, so the degree is n. Graph is continuous and smooth and continuous. There is no hole, there is no sharp corner, there is no discontinuity. Maximum number of turning points is n minus 1. Turning points refer to max and mean extrema. At a zero of even multiplicity, the graph of f of x touches the x-axis. That means it can cross the x-axis. At a zero of odd multiplicity, the graph of f of x crosses the x-axis. Between zeros, the graph of f of x is either above or below the x-axis. And behavior for large values of x in an absolute value, negative or positive, the graph of f of x behaves like the graph of its leading term, y equals a sub n x to the power of n. So this is the one that matters ultimately. The real zeros of a polynomial function. Here's the division algorithm. N of x divided by d of x is q of x plus r of x over d of x. Or n of x is q of x times d of x plus r of x. Dividend is quotient times the divisor plus the remainder, where either r of x is 0 or the degree of r of x is less than the degree of d of x. That's when you stop. And of course, if r of x is 0, that means it's a factor of n of x. The remainder theorem says if we divide f of x by x minus c, we can find the remainder by evaluating the function at c, f of c. The factor theorem says if we do that and we end up with 0, x minus c is a factor of f of x. If f of x is a polynomial function or any continuous function, and if for real numbers a and b, the values of f of a and f of b are opposites in sign, then there exists at least one real zero between a and b. So the idea is that f of a and f of b have opposite sides. One is negative, one is positive. Since 0 is in between and we have a continuous function, it has to cross the x-axis at some point. The rational zero theorem. rational zeros. If f of x is a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 all the way to a sub 0, which means if it's a polynomial, with integer coefficients, if p over q is the lowest term is a rational zero of f of x, then p is a factor of the constant term a sub 0 of f of x, and q is the factor of the leading coefficient of a sub n of f of x. Meaning what? This is the constant. You write all the factors of that as the numerator. This is the leading coefficient, a sub n. You write all its factors, and the ratio would be possible rational zeros. Number of zeros theorem. A function defined by a polynomial of degree n has at most n distinct unique complex zeros. Remember, complex numbers are in the form of a plus bi. Descartes' rule of sign. Determine the number of positive and negative zeros. Let f of x be the above polynomial function with terms in descending powers of x. The number of positive real zeros either equal the number of variation in sign occurring in the coefficient of p of x, or is less than the number of variation by a positive even integer. The number of negative real zeros either equals the number of variation in sign occurring in the coefficient p of minus x, or is less than the number of variation by a positive even integer. Bound on zeros theorem. Let p of x define a polynomial function of degree n greater than or equal to 1 with real coefficients and with positive leading coefficients. If p of x is divided synthetically by x minus c, and if c is larger than 0, and all numbers in the bottom row of the synthetic division are non-negative, then p of x has no zero greater than c. C is considered to be the upper bound. If c is less than 0, and the numbers in the bottom row of the synthetic division alternate in sign with 0 considered positive or negative as needed, then p of x has no 0 less than c. C is the lower bound. For section 3.4, complex zeros, fundamental theorem of algebra. Fundamental theorem of algebra says every function defined by a polynomial of degree 1 or more has at least one complex, that means real or imaginary, zero. If p of x is a polynomial of degree 1 or more, then there is some number k such that p of k equal to 0. So therefore, p of x is x minus k times q of x, where q of x can be also factored, resulting in p of x being a times x minus k1 times x minus k2 all the way to k sub n. So every complex polynomial function f of degree n larger than or equal to 1 can be factored into n linear factors, not necessarily distinct, of the form f of x equals a sub n times x minus r sub 1 times x minus r sub 2 all the way to r sub n, where a sub n, r sub 1, r sub 2 all the way to r sub n are complex numbers. That is, every complex polynomial function of degree n larger than or equal to 1 has exactly n complex zeros, some of which may repeat. And that repetition is really important to understand when we say we have n zeros. If something repeats, that count, the multiplicity counts. Conjugate zeros, theorem. If P of X defines a polynomial function having only real coefficients, and if R equals A plus BI is a zero of P of X, then its conjugate, we call it sometimes R bar or just R conjugate, is A minus BI is also a zero of P of X. Corollary. A polynomial function P of X of odd degrees having only real coefficients has at least one real zero. Why is that? Let's make sure everybody understands the reason for it. The conjugate zero says if we happen to have an imaginary zero, it happens in pairs. So if A plus BI is there, so is A minus BI. If the degree is even, it could be that all of them are complex conjugates. But if it's odd and they happen in pairs, then one will be at least a real zero. So the reasoning, because imaginary ones happen in pairs. Complex conjugate zeros happen in pairs. Every polynomial function with real coefficients can be uniquely factored over the real numbers into a product of linear factors and or irreducible quadratic factors. What do we mean by all of that? Let's find out. Find a polynomial function with specified zeros. Find a polynomial f of degree 4 whose coefficients are real numbers and that has the zeros 1, 1, 4 plus I. When it repeats, that means 1 is being repeated. That means the function has a factor of x minus 1 quantity squared. That's the meaning of it, everybody. Okay? Now, this has a degree 4 and it must have 4 zeros. Since 4 plus I is a 0, so is 4 minus I. Since 4 plus I is a 0, by the conjugate pairs theorem, 4 minus I is also a 0. So those are the 4. So for 1, we write x minus 1. For this one also, we write x minus 1, or we can just write x minus 1 squared. How do we write for this one? X minus this, and then x minus this in the following manner. Pay attention to what we are going to write. You could write, you could just get rid of this and write x minus 1 squared. It's up to you. But in any event, I want to make sure we understand how we take care of this. X minus this times x minus that. And we are going to do the math. I'm going to show you an easy way to do this. Of course, we do know the answer here is x squared minus 2x plus 1. I want to show you how to multiply this. You have two choices. Multiply the x by the brackets, then negative 4 by the brackets, then negative I by the brackets. Or this is minus 4 minus I. This is minus 4 plus I. And put x minus 4 together. And so please understand why I'm doing this, because I want to remind you when you have a minus bi times a plus bi, you get a squared plus b squared. I hope you remember that. Therefore, the result is when you multiply the two brackets, this is x minus 4 squared, this is plus 1 squared according to this. So how fast we can do that? Okay. I hope you see that. Now, we should know this is x squared minus 8x plus 16. With this one, they get to become 17. Again, we all know a plus b squared is a squared plus 2ab plus b squared. And if we happen to have a negative sign here, that goes here. And now I'm going to give you the last step. You just multiply the x squared by this minus 2x and then plus 1. Combine terms. I'm not going to go through that. The only reason I wanted to show you this, I wanted to make sure you understand how to handle this, how to write this, and then how to multiply by this methodology. This will speed up the process. Okay, everybody? Very straightforward. As far as multiplying them through, you know how to do that. I mean, I can show you the intermediate step quickly, but so this is a, then if we go with x squared, we get x cubed, I'm sorry, x to the power of 4, x to the power of 4 minus 8x cubed plus 17x squared. Now negative 2x gives us negative 2x cubed plus 16x squared plus 17. Now the 1 just repeats the second parentheses, x squared minus 8x plus 17. And you can combine them. You see that 17x squared and 16x squared and x squared gives you 34x squared. The rest of them are easy to see. So you can combine. You just this one, and this one. And this one, I think I minus that this is negative 34x.
Professor, I had a question.
Yeah.
Oh, no, wait, never mind. You fixed it. I was going to say,
Yeah.
wouldn't that one be 34x?
Yes, you're 100% right. So the key again is to pay attention to the way you multiply these two. You want to multiply in this fashion by putting x minus 4 together and minus I and plus I, so you can use the easy way out. Find the complex zeros of a polynomial function where f of x is x to the power of 4 plus 2x cubed plus x squared minus 8x minus 20 and write in factored form. So we're going to cover the synopsis of the previous section by first noticing this is degree 4. And therefore there are 4 complex zeros. Then we use the rational zeros theorem and we try to find potential zeros, noticing that this is a sub 0, hard to see it here. This number is a sub 0, and 1 is a sub n. So factors of a sub 0, which is negative 20, over factors of a sub 1, which is 1. And I want you to know, factors of 1 is plus minus 1. So whenever you come up here, divide by it, you get the same thing. For negative 20, factors are plus minus 1, plus minus 2, plus minus 4, plus minus 5, plus minus 10, and plus minus 20. I hope everybody can see what I'm talking about. What does this mean? If there is any rational zero, remember rational numbers are in the form of a fraction where the top and the bottom both are integers. If so, has to be among these numbers. So since we know that, we can check them out. And the way we check them out, for example, we plug in 1 to see what we get, negative 1, what we get, 2, what we get. And as long as we get a couple of them, then we move on. So let's plug in 1. If we plug in here 1, we get 1 to the power of 4 plus 2 times 1 cubed plus 1 squared minus 8 times 1 minus 20. This is 1, this is 1, that means 2 and 1, that means 4 minus 8 minus 20 minus 24. This is not 0, which means x minus 1 is not a factor. You can try another one. I'm going to leave it for you to show that a 2 gives you 0. In other words, if you plug in 2 into this, you will get 2 to the power of 4 plus 2 times a 2 cubed plus a 2 squared minus 8 times 2 minus 20. They do add up to 0. You can check it out. Since f of 2 is 0, that means there is a factor of x minus 2. We are going to do synthetic division. And here's how the synthetic division works. I want to make sure you remember that. You just write the coefficients. Let me just erase the mess. 1, 2, 1, negative 8 minus 20. And if there is any missing term, let's say this was missing, you have to put a 0 as a placeholder. Unlike long division, that if you don't and you're careful, it will work. In the case of a synthetic division, it doesn't. So 1, 2, 1, negative 8, negative 20, because nothing is missing. And you put the 2 here. You drop the first one. Then you multiply 1 by 2. You put it here. 2 and 2, they add up to 4. You multiply by 2, becomes 8, and 1, you get 9. Multiply, you keep on multiplying by this number. 9 times 2 is 18 and negative 8, 10. 10 times 2 is 20 and negative 20 is 0. Because it's 0, because you have 2 ways to show that: synthetic division or factors theorem. A factors theorem, that means prove that f of 2 equal to 0. Now, this one has degree 4, so this one has degree 3 because we go down by that. So it's the product of this thing. I said it's x minus 2, and now this one is x cubed plus 4, x squared plus 9x plus 10. So this is what we get. Again, x minus 2 because f of 2 is 0. And this comes from the bottom row. Now, if this was of degree 2 class, you could do by factoring quadratic formula. Either way is fine. Since it's of degree 3, we're going to continue. And since we don't want to waste time, we work with something that is going to work out. Number -2. Remember, these are potential rational zeros, so -2 will do the job. So these numbers 1, 4, 9, 10 go here. You drop the 1, and then you multiply this one by -2, meaning multiply this by -2, and add them up, you get 2. Multiply by -2, and add them up, you get 5. You multiply by -2, you add them up, you get 0, meaning, now this means there is a factor of x plus 2. So now the next one would be x minus 2 times x plus 2. And this one, now this goes down by 1. So this is x squared plus 2x plus 5. So this last one gives you x squared plus 2x plus 5. This gives you x plus 2. This gives you x minus 2. Because the degree is 2, we're not going to continue by checking. We just handle it by one of the methods that we've learned. In this case, we will go with the quadratic formula. The first one is 0, the second one is 0, this one is 0, and you use x equals minus b plus minus a squared of b squared minus 4ac over 2a, because it can't be done by factoring. So let's recap. So we used the 2, and we ended up with 0, so x minus 2 times what we have here. Use the -2, we ended up with 0. That's a factor. So x minus 2 and x plus 2 times whatever is left here. And since we are interested in finding all zeros, we said this equal to 0. This is clearly 2. This is clearly -2. What about this one? Well, A is 1, B is 2, C is 5. We plug in minus a B, so minus 2 plus minus the square root of B squared 2 squared minus 4A, which is 1, C, which is 5, and we get 4 minus 20 or -16, and becomes minus 1 plus minus 2i. Let me show you why this is the case, because this becomes minus 2 plus minus 4i, and as you can see, you can divide by 2. This gives you -1, this gives you plus minus 2i. So what are the zeros? You have 4 zeros. One of them is 2, one of them is -2, and these are, as of course expected, happening in pairs. -1 plus 2i, -1 minus 2i. We want to write this in factored form. We already have these 2. Then we're going to say x minus this times x minus this. So x minus -1 plus 2i and x minus -1 minus 2i. If we were to multiply them out, we already know the answer. I showed you that you combine this one with this one and separate this one. The same thing here. In order to be able to use a minus b times a plus b is a squared minus b squared. That's the only reason. Otherwise, you don't have to. Find the complex zeros of a polynomial function, where f of x is 3x to the power of 4 plus 5x cubed plus 25x squared plus 45x minus 18, and write it in factored form. And the degree is 4. We have 4 complex zeros. What are the possible zeros? According to the rational zero theorem, factors of a sub 0, this is a sub 0 minus 18, over factors of a sub n, which is 3. By the way, a sub n is a sub 4 because the exponent is for a sub 4. Okay. And so factors of 3 are plus minus 1 and plus. So let's just write them actually. So we have this. The bottom is plus minus 1 plus minus 3. That's for number 3. For 18, negative 18 or 18. Let me use a different color. Plus minus 1. Plus minus 2. Plus minus 3. Plus minus 6. Plus minus 9. Plus minus 18. When we divide them by plus minus 1, we get the same as the numerator. When we divide them by 3, plus minus, we get plus minus 1/3, plus minus 2/3, plus minus 1, we already have it, plus minus 2, we already have it, plus minus 3, we already have it, plus minus 6, we already have it. So these are the possible zeros. And so again, rational zeros theorem gives us possible rational zeros. Doesn't mean these are the zeros. That means if there is a rational zero, must be among those. That's it. You have to check, everybody. You have to plug in 1, you have to plug in -1, 2, -2, and so on until you hit 0. Again, we don't want to go through the process. So let's start plugging in something that works. If you plug in -2, we get 3 times -2 to the power of 4, 5 times -2 cubed, 25 times -2 squared, 45 times -2, minus 18. And you can verify that they add up to 0. I mean, just in case, a couple of them, that's, so, this is 16, 48, minus 8, minus 40, positive 4, 100, minus 90, minus 18, and you get to 0. Okay. What does it mean? We got one of the factors, x plus 2. We are going to divide this by x plus 2. We get 3x cubed minus x squared plus 27x minus 9. I'm assuming you guys can do this division. So you divide this by x plus 2. And when you do that, either with the long division or synthetic division. Synthetic division is the fastest way. Again, I just get that started for you, and then you finish it. So let's see, what color do we want to use? So we put here -2, and then here the first number is 3, then it's 5, then it's 25, 45, and the last one is -18. And before we move on, I want you to see that x to the power of 4, x to the power of 3, x to the power of 2x, and a constant. There is nothing missing. Again, let's assume this wasn't there, then you had to put 0 instead. Instead of this, we would put 0 if this was missing. So there is no missing term. And of course, what happens? You drop this just the way it is. You multiply it by -2. You get -6. These two add up. You get -1. You multiply it by -2. You get +2. You get 27. You multiply it by -2. You get -54. You get -9 times -2. You get +18 and 0. This is how you get this. Okay, actually, I went through the whole thing. In any event, so we have that. Now we can continue looking at more zeros. It so happened that we can do this factor by grouping. If you group this together as follows, group these two, x squared comes out as x squared times 3x minus 1. Group these two, 9 comes out as 9 times 3x minus 1. So we are looking at this part, okay? And this becomes 3x minus 1 times x squared plus 9. If you set this one equal to 0, x is 1/3. If you set this equal to 0, x squared is minus 9. X is plus minus 3i, maybe, so let me just quickly show you this one. If you set this one equal to 0, gives you that. This one will give you x squared equals -9. X is plus minus 3i. So we have all the complex zeros, plus minus 3i, -2, and 1/3. So this is two of them that are imaginary, plus minus 3i. This is one of them. This is another one. Both of them are real. So two real parts and two imaginaries. So if we want to write this as a factored form, we're going to write this is equal to we can factor the 3 out. Notice if we use those, and let's do them. Ignore that for now. X plus 3i, x minus 3i. That's this part. X plus 2x minus 1/3. I hope you recognize that. Ignore that. For now, ignore it. Different color. Ignore it for now. If you write this, Just look at the very first terms. And you multiply x by x by x by x, you get x to the power of 4, not 3x to the power of 4. Because it's 3, you have to put the number, whatever this number is, you have to put it here. And if you go through the process, if you multiply these two and then by those two, you see you get the same answer here. In fact, if you look at this one, let me erase the whole thing again. If you look at this part, everybody, this is the same as this times this, okay? Because when you write in factored form, you write x equals 1/3, and you keep this as x. Now, x minus 1/3 times 3 is the same as 3x minus 1. That's why. So you want to be careful with that. Find the remaining two zeros of a polynomial of degree 6 whose coefficients are real numbers and has the following zeros: 2, -3, 2i, and 1 minus 2i. We have total of 6 zeros because the degree is 6. The conjugate theorem says because 2i is a solution, is a zero, so it's the conjugate -2i. Also, the conjugate theorem says because 1 minus 2i is a zero, so it's 1 plus 2i. And now we have all of them. We have 1, 2, 3, 4, 5, 6. So from 2i, we got -2i. From 1 minus 2i, we got 1 plus 2i by the theorem, conjugate theorem. Find a polynomial of degree 5 whose coefficients are real and has the zeros 0, -2i, and 2 plus I. Well, this means x minus 2i means we have one more, 2i, right? So we use the 0, and by the way, we start with a because we don't know. Minus 2i gives us x plus 2i. And since this is a 0, so is 2i, everybody. So that gives us x minus 2i. Then the way we write this is x minus this piece. So x minus the parenthesis 2 plus I. Because 2 plus I is a 0, so is 2 minus I. 2 plus I is a 0, therefore is 2 minus I. And for this one, we're going to write x minus the parenthesis 2 minus I. Again, if you wanted to multiply them out, and that's what you want to do, and I leave it for you to do that, here's the methodology. Let me grab a different color here. You should do x minus 2 minus I here. And let me use a different color. Over here, you would do x minus 2 plus I. And just this part becomes x minus 2 when you do the product squared plus 1 squared. And that's actually x squared minus 4x plus 4 and 1 is plus 5. And these two, let me use a different color, and these two, you get x squared plus 2 squared. That means x squared plus 4. So you have a times x squared plus 4 times x squared minus 4x plus 5. Let me write that for you. So it would become equals ax x squared plus 2 squared is 4. X minus 2 quantity squared is x squared minus 4x plus 4, and then 1 squared makes it plus 5, okay? X squared minus 4x plus 5, and this would be the final answer, x to the power 5 minus 4x to the power 4 plus 9x cubed minus 16x x squared plus 20x. You can try this on your own. Again, reminding you, k is a zero of a polynomial function if p of k is equal to 0. Is 2 a zero of the function f of x equals x cubed minus 4x squared plus 9x minus 10? What about negative 2? Use a calculator. Just by hand, just plug in 2. If it gives you 0, yes. If it doesn't, no. Plug in negative 2, the same thing. This is done. But if you were to do it by a calculator, I just wanted to show you the concept. Is a number a 0 value, you use y equals f of x, and you enter function in y1. Okay, in this case, x cubed minus 4x squared plus 9x minus 10. Then click vars, variables, number one function, y1 appears, and put the number, okay, like so, vars, okay, function, and then y1, okay, and you put 2, and it evaluates it for you because it's called y1, that's why, okay. It gives you 0. You also calculated with negative 2. This means yes. Is 2 a 0 of the function? Yes. Now plug in negative 2. You get anything other than 0. It doesn't matter what number. Something that is 0, yes. Something that is non-zero, no. So yes, this one works. No, this one doesn't. If you were to use a calculator. Finally, I want to remind you of the question we did before, and it's helpful for this one. Use number of zeros theorem and Descartes' rule of sign to discuss the real zeros of the function f of x. In this case, we want to discuss all zeros, including imaginary. So here's what Descartes' rule of signs tell us. You look at f of x and the signs, just the sign. This is 3, that means positive. This is negative 4, that means negative. This is positive 3, positive, positive, negative, negative. So you, by the way, n is 7, maximum number is 7. So you put those signs. When does the change happen? Well, from here to here, we have one change. Positive to negative, one change. Negative to positive, one change. But there is no change here. They are both positive. Positive to negative is another change, and there is no change here. So we have one change here, another one here, another one here, and we have total of 3 changes. Which means the number of, what does that mean? The number of positive real zeros is either 3, or you go down by 2. You always go down by an even number. So 3 or 1, and there's no number less than that. You can't go negative. That's for the positive. What do you do for the negative? Replace the x with negative and calculate f of negative x. So 3 times minus x to the power of 7 becomes minus 3x to the power of 7. Minus 4, this remains the same because it's even. This changes to negative 3 because it's odd. This remains the same. This changes to plus x. This doesn't. So I'm assuming everybody can evaluate this. Now, let's look at the signs only. Negative 3. We just want the sign. Negative. Negative. Again, negative. Positive. Positive. Negative. Just look at the signs. Nothing else. So, negative to negative, no change. To this negative, no change. To this positive, there is a change. From this positive to positive, there is no change. From positive to negative, there is a change. So there is a change here and here. So how many changes? 1, 2. What does it mean? So positive real zeros, we have 3. Negative real zeros, we have how many? 2. If we go down by 2. This may go down by 2 becomes 1. This may go down by 2 becomes 0. However, we said we have total number of 7. Maximum number of zeros is 7. 7 complex zeros. So the rest of the zeros must become imaginary. Okay, part of the complex. So if you look at these 2, they add up to 5. So we must have 2 imaginary zeros for them. If we have 3 zeros that are real, 2 that are negative, 2 must be imaginary. Over here, if we have only 1 positive and no negative, all of the rest, that means 7 minus 1, 6 of them must be imaginary. We should recognize that.